his Farbenlehre, which he regarded as the equal of his entire poetic epos, was by and large dismissed by all his contemporaries and has remained in a sort of limbo ever since, seen as the whimsy, the pseudoscience, of a very great poet. So here the author introduces this German poet, Goethe, and talks about this poet's small contribution towards science, color theory specifically, called Farbenlehre, but goes on to say that the poet Goethe's contemporaries dismissed his scientific thoughts. They thought he was a very great poet, a wonderful poet, but not a scientific thinker. But science itself was not entirely insensitive to the anomalies that Goethe considered central, and Helmholtz, indeed, gave admiring lectures on Goethe and his science on many occasions, the last in 1892. So now the author has introduced this other character, this other person, Helmholtz, who was a scientist, a 19th century scientist, who actually considered Goethe's views on color theory interesting and important. So we have a juxtaposition here between Goethe's contemporaries, who thought he's just a poet, but he didn't have much interesting to say on science, versus Helmholtz, who actually thinks Goethe had a good contribution to make to science. Helmholtz was very conscious of color constancy, the way in which the colors of objects are preserved so that we can categorize them and always know what we are looking at, despite great fluctuations in the wavelength of the light illuminating them. The actual wavelengths reflected by an apple, for instance, will vary considerably depending on the illumination, but we constantly see it as red nonetheless. This could not be, clearly, a mere translation of wavelength into color. There had to be some way, Helmholtz thought, of discounting the illuminant, and this he saw as an unconscious inference or an act of judgment, though he did not venture to suggest where such judgment might occur. Color constancy for him was a special example of the way in which we achieve perpetual constancy generally, make a stable perceptual world from a chaotic sensory flux, a world that would not be possible if our perceptions were merely passive reflections of the unpredictable and inconstant input that bathes our receptors. So this passage is talking a little bit about the science behind sight, the science behind being able to see things, particularly see things in color. So if we see an object, for instance an apple, the reason we can identify it as red is because the light hits the apple and red light bounces back to our eye, so we're able to see that red color, we're able to see the color of the apple. But what Helmholtz is pointing out here is that we can shine different kinds of light on the apple, different wavelengths, and regardless, our eye will identify that apple as red. So this doesn't seem to make purely scientific sense. We would expect if we shine a different kind of light on the apple, we might see a different type of color reflected. So why do we consistently see the apple as red? That's the color constancy that Helmholtz was talking about, and his idea discounting the illuminant. This is important to this particular essay, discounting the illuminant. The illuminant is the type of light that is shining on the apple, so the type of light that allows us to see the apple. But Helmholtz is saying that when we detect the color of the apple, we by and large discount the illuminant, so it doesn't really matter what kind of light we shine on the apple, we're still able to see it as red, and that's a very strange concept to think about that Helmholtz was very intrigued with. Helmholtz's great contemporary, James Clerk Maxwell, had also been fascinated by the mysteries of color vision from his student days. He formalized the notions of primary colors and color mixing by the invention of a color top, the colors of which fused when it was spun to yield a sensation of gray, and a graphic representation with 3 axes, a color triangle, which showed how any color could be created by different mixtures of the 3 primary colors. So now we've been introduced to another scientist, Maxwell, and Maxwell did some important contributions to color. For instance, the idea that there are primary colors and secondary colors, and we can create any secondary color by mixing together the primary colors. We've all probably seen a color wheel that shows how you can mix, for instance, red and blue to get purple, yellow and red to get orange, and so on to get all of the different colors. These prepared the way for his most spectacular demonstration, the demonstration in 1861 that color photography was possible, despite the fact that photographic emulsions were themselves black and white. So in 1861, there was no way to print an image in color. It could only be printed in black and white. Yet Maxwell was able to make color photographs. How so? Let's read on and find out. He did this by photographing a colored bow 3 times through red, green, and violet filters. Having obtained 3 color separation images, as he called them, he now brought these together by superimposing them upon a screen, projecting each image through its corresponding filter. The image taken through the red filter was projected with red light, and so on. Suddenly, the bow burst forth in full color. So Maxwell was able to take 3 different images of an object, a bow, using different color filters, and then shine light through those filters later on to produce a colored image. Clerk Maxwell wondered if this was how colors were perceived in the brain, by the addition of color separation images, or their neural correlates. What functions in the brain as a color separation image, as in his magic lantern demonstrations. So our brain does a similar thing. It breaks down the different kinds of colors we're seeing to produce the actual image of the object that we're looking at. So for instance, an apple or a bow. Clerk Maxwell himself was acutely aware of the drawback of this additive process. Color photography had no way of discounting the illuminant, and its colors changed helplessly with changing wavelengths of light. So here we hear that phrase again, discounting the illuminant. So the method that Maxwell used for color photography was highly dependent on the type of light that he was shining through the filters. If he shone a different type of light, the object would appear differently. So it's not exactly the same as how the brain works in discounting the illuminant, as Helmholtz had talked about earlier. In 1957, 90-odd years after Clerk Maxwell's famous demonstration, Edwin Land, not merely the inventor of the instant land camera and Polaroid, but an experimenter and theorizer of genius, provided a photographic demonstration of color perception even more startling. Unlike Clerk Maxwell, he made only 2 black and white images, using a split beam camera so they could be taken at the same time from the same viewpoint through the same lens, and superimpose these on a screen with a double lens projector. He used 2 filters to make the images, one passing longer wavelengths, a red filter, the other passing shorter wavelengths, a green filter. The first image was then projected through a red filter, the second with ordinary white light, unfiltered. One might expect that this would produce just an overall pale pink image, but something impossible happened instead. The photograph of a young woman appeared instantly in full color: blonde hair, pale blue eyes, red coat, blue-green collar, and strikingly natural flesh tones, as Land later described it. Where did these colors come from? How were they made? They did not seem to be in the photographs or the illuminates themselves. These demonstrations, overwhelming in their simplicity and impact, were color illusions in Goethe's sense, but illusions that demonstrated a neurological truth, that colors are not out there in the world, nor, as classical theory held, an automatic correlate of wavelength, but rather are constructed in the brain. So what happened here? We have a new scientist, Land, who invented a new type of photography where he was able to take two images through the same camera. It had a split lens, so it could get two images at once through different filters, red and green, and then projected the images using red light for the image made from the red filter and regular plain old white light for the image made with the green filter, and this actually produced a full color image. That's not intuitive because we would expect the image to appear red if we're only projecting it with red and white light. However, this proved all the way back to Goethe, the first poet we talked about, and his idea of the brain, perceiving the colors in a very specific way. It proved that that was actually the right way to think about it. Our brain was able to pick up the right colors, disregarding the illuminate, so even though we weren't shining those particular colors. So this was a very interesting concept in color theory that all came about because of these many different contributions from scientists and even some poets.